Hello guys, welcome back to MedZone African Motives, still on our revisions for Engineering Science N2, and this is going to be a full paper for the exam, which was for April 2024. So we are going to consider our question paper. Make sure that you do go through your instructions and information when answering your questions, especially that you are supposed to have your answers. If you are to you have your calculations, you are supposed to show these 3 steps, okay? The first one, the formula that is used, and the manipulation that you're going to, or the manipulation thereafter, and also the substitution, the answer together with the correct SI unit that is to be given. All right, then also remember your values that you're going to use in the simplification. We're going to talk about that. If there's a question which needs us to use these basic values that you are given there, then we have to apply that part. All right. So the first question that we are given is on dynamics, and that is the first part, 1.1, to differentiate between a scalar quantity and a vector quantity. All right. So this one is just a repetition of the question that is always like that, and you have to know this. Remember, a scalar quantity, we're talking about something that has got magnitude here. It has got magnitude only. So you talk of the magnitude only in this case. While a vector, this one, it has got both. So the vector, it has got both magnitude. All right, so let's do this here. So this one has both magnitude and direction. So we are going to have 2 things in this case, the magnitude and direction. But in this case, differentiate, you write this as a statement, that is a scalar quantity has magnitude only, while this, which is the vector quantity, has both magnitude and direction. So that was your question. Define the term velocity. Velocity from our displacement. This is the rate of change of displacement. So we are talking of the rate of change. The rate of change of displacement. So remember, this is measured in meters per second displacement over time. So that was 1 mark for that. 1.3, the diagram below describes the motion of a body taking place in a straight line. Thus, displacement versus time. So we're talking about displacement in meters, time in seconds. All right. So this is the motion that you're given. So we are talking about a displacement versus time graph. 1.31, determine the velocity during the first 8 seconds. So during the first 8 seconds, if we are to consider this our time at 8 seconds, it corresponds here straight to a certain displacement. So given displacement and given time, we can find the velocity. Remember our definition here, the velocity is the rate of change of displacement. So if it is the rate of change of displacement, that means we are considering the displacement over the time. So that is our condition there. So our velocity is simply the change in displacement over the change in time. And in this case, the displacement is corresponding straight at 160 meters, and the time at that point where we are given 8 seconds. So that was going to give us the velocity. As we know, guys, velocity in meters per second. So you can also write even this as 20 meters per second this way. So that was your velocity. Describe, that is on 1.32, the movement between the 8th and 12th second. Describe the movement between this 8 and 12. In terms of the movement there, it is 160. At this point, it is still 160. So what is it? But the time has changed. It was at 8, we are still at 160. At 12, we are still at 160. The time changed, but what is happening in terms of the movement? In terms of the movement, there's no movement in that case. There's no change in movement. There is no movement in this case. So in this case, we talk of no movement. There is no change in the movement. 160, we are still at 160, which meaning to say there is nothing that changed. If you check here, there's a movement that is, we are increasing 0.48 up to 120, up to 160. Then it maintains that no movement between this time. Then the movement starts again 160 meters to cover up from this point up to this point. It's 160 meters. Then another 80 meters there, another section down here representing 80 meters, but in the negative region. But it's a displacement which is taken. So in that case, you must understand your diagram. 1.33, you are given, determine the total distance traveled from the diagram. So the total distance from the diagram, you consider to say, this line going up, it covered up to 160 meters. All right, so this is 1.33. So our distance will be 160. Then from there, up from this point up to this point, like I explained before, even though we are going down, but that is 160 meters covered. Again, we move from this point. Remember, this is at 0 here. So from 0 going down, we are going up to -80 there. We have to add up everything. So that is 80. So that is our distance in meters covered, which is 400 meters. All right, that is from the diagram. The displacement from the diagram is the one that you take in the opposite region. Not this side, but the opposite region that we are seeing. So in the opposite region, we are talking of a -80 meters, which is 80 meters that we are talking about. So that is going to be 80 meters in the opposite direction. In opposite direction. So like I said before, you need to understand, most of you guys are used to just the velocity time graph. No, it can be a distance time graph, not just a velocity. It can be a distance time graph, like what, a displacement time graph, like what we are seeing there. 1.4, we are given a brick is dropped vertically downwards, all right? From the top of the building at this velocity, which is our initial velocity of 3 meters per second, to reach the ground after 5 seconds. The time frame to reach the ground is 5 seconds. As we know that as we are going down, there is a gravitational acceleration to be considered, G, 9.8 meters per square second. So calculate the height of the building. So the height of the building is same as S, which is the displacement. But in this case, you use the S in terms of the formulas that you are given. Remember your formulas, they are given in terms of S. So we are going to consider on these formulas, which one can we work with? All right, so let's say this one, S is equal to UT plus half AT squared. But remember, we are no longer having this as acceleration, as a normal acceleration. This is now to be represented with a gravitational acceleration whenever you are given that condition. So I think this can work because we have got U, T, and this. So we can calculate S, which is representing the height. But in this case, that is your displacement. So S from the formula is given as UT plus half AT squared. So according to what we have, this is the best formula that we can use, where there is initial velocity, time, and acceleration. This is acceleration, only that it's a special type of acceleration, gravitational acceleration, but it's acceleration. So remember, as you are going up, it is opposed to be taken as negative 9.8. But as you are going down, you're moving in the exactly, guys, this gravitational acceleration is to oppose. As you are going up, it is opposing going down. So as you are going down, you are moving in the same way with that gravitational acceleration. So you use it as a positive in that sense. So in this case, our S was going to be UT, our initial velocity 3 times the time, which is 15 plus half of, remember, say this is now G for the gravitational acceleration. That is 9,8 times t squared, the time, which is 5 squared. So this is on its own. So meaning to say, you combine everything, that was going to give us S, which is the displacement, but that displacement, it represents the height in that case. So that is our height, which is the height of the building that we are given there. But what you are using, displacement formula. In meters, that is the height. So you must be careful with what you are working with on the information that you are given. All right, so let's consider another part of our question 1.5. An object is accelerated uniformly that is our initial velocity. So we're given an initial velocity of 36 kilometers per hour to which is our final velocity of 105 kilometers per hour in 12 seconds, which is the time frame, time in seconds. Calculate the acceleration of the object. You do not know the acceleration. So take note the units that you are given there must be converted to the meters per second. And we are given that 1 meter per second is equal to 3,6 kilometers per hour. With this conversion, we can convert. With this conversion, 1 meter per second is equal to 3,6 kilometers per hour. So meaning to say when given 35, you divide by this. This is 35 will be this side. So you divide by 3,6. So just divide by 3,6. That was going to give us 9,722 meters per second. The same thing, you divide here by 3,6. That was going to give you 29,167 meters per second. Remember to 3 decimal places, you're rounding off. So with these, we can calculate the acceleration. Just like the previous case, we have to look for the formula which is suitable where we are given these. So if you are to consider, we can use this formula V is equal to U plus, because we've got final velocity, everything is there. V is equal to U plus 80. We do not have S, we do not have this displacement S, so you cannot focus with this part where there is S or this part where there's S. This is where we have got everything in that case, so we can consider that, calculate our acceleration. So from that formula, V is equal to U plus 80. You want acceleration, you can make it the subject, just transpose this. It'll be a minus, that's V, minus U is equal to 80. You are multiplying by this acceleration, so divide. Okay, so sorry, we need acceleration, so divide by the time to remain with acceleration. So you divide here, you remain with acceleration. So in actual sense, our acceleration is equal to V minus U over T. So you can substitute what we are given from our information. The velocities in meters per second, our V, 29,167 minus U, which is 9,722, everything over the time, which is 12. So this was going to give you the acceleration of the object, which is 1,620 meters per square second. So for the units, you can also write this as meters per square second like that. So it's still the same thing. So this is how your questions are given. You must be careful with the information that you are given. How are you going to attempt your questions in whatever sense that you're given? The formulas, if you are stuck, the formulas are there for assistance. You can go through your formula sheet. All right. Question 2.1, which is on statics. Define the term resultant of forces. What is it that you're talking about? So remember, the resultant of forces you're talking about when a single force, that single force that we are talking about, is that this resultant. So we are simply referring to it as a single force. So this one, it is a single force that can replace, that can replace. So this one is gonna replace 2 or more forces. So it's gonna replace 2 or more forces and still have some effect. Have some effect. So it must have the same effect as all the applied forces. All right, so this was what we're given. You can just save your own definition that you understand, guys, okay? Then on 2.2, you're given, this is a uniform beam that we are given, which is 16 meters long, carries concentrated or point loads of, all right, so we need to draw this on 2.2. So guys, there's no way. Let us, as we are reading this information, we'll be drawing our diagram because there we need to understand like what is happening there. Okay, so this is it. Just gonna try and see if I'm going to win. You know, these softwares, guys, sometimes they just tend to misbehave, but just hope it's not gonna misbehave today. All right, so we're just gonna take our uniform beam like this, okay? I think it's gonna be fine. So let's see what you're given. So this is 16 meters long. It carries, what is it that it has? The concentrated or point loads 160 Newton and 70 Newton at distances 2 meters and 6 meters respectively from the left-hand side of the beam, from the left-hand side. So let's start with the first one, which is 2 meters from the left side. So that is our 160 Newton, 2 meters. Remember, it's respectively. So 160, 2 meters from the left side, okay? So we need 2 meters from the left side, okay? So you're going to have something like this. Sorry for that, guys. Sorry for that. I need that diagram. So that is the effect now of these softwares, guys. You try to be fast, but they'll tend you to be slow. So anyways, let's see. So you're gonna have something like this. Remember, we just need a point load 2 meters from the left side. So just something like that, okay? But I'm just gonna, guys, have a sketch so that you just understand me in this case. So maybe something like this. This is 2 meters from the left side, okay? 2 meters from the left side, and it is of 160 Newton. So that is 160 Newton. And let's see the other one. It is 70 Newton, 6 meters, still from the left-hand side, but this one is 70 Newton. So 6 meters, meaning to say there we have covered 2. How many meters are we going to need to cover 6? 2 plus 4, that is 6. So meaning to say in between, we are going to have another point load of 70 Newton, which is 4 meters in between this one, but 6 meters from the end. Like if you cover from the end, this will be 6 meters. 2 plus 4, that's 6, okay? Let's see the other one. We are then given from there, there is also a 250 point load. It's a point load again, okay? 250 Newton point load at the right end. So this one is direct at the right end. At the right end here. This is your right side. At the right end, there is a 250 Newton, okay? At the right end. Then we are given support L is on the left end. Okay, so L is on the left end. This is the left side. There is a support here. Remember, a support is going up. That's a support which is on the left end. And another support R is 1 meter from the right end of the beam. 1 meter from the right end, from this side, 1 meter going this side. So maybe somewhere there, that is where we have got our 1 meter. we have got a support from this side. So this is it up to the end. So that is 1 meter. So let's go back to this part that you're given. Remember, this whole section, it is 16 meters. From one end to another, it is 16 meters. So if you have covered 1 meter here, what does it mean? It means in between, there is going to be 15 meters. 16 minus 1, that is going to be 15 meters. So that if you add these two, they add up to 16. So that's it. You can analyze your diagram, but in terms of just drawing this, just this is enough. This is enough. Yes, you can even show us what is in between these, what is in between this, but it's not necessary. This is enough. Okay, so that was your diagram. And from there, you are going to now calculate the magnitude of the reactional forces L and R by taking moments about each support. About each support. So let's start with the first one, okay? So this was our 2.21. Let's consider this time 2.22. So as we are told, we are supposed to take our moments about each support. So in this case, we're going to start by taking moments about L. Okay, so taking moments about L. Okay, so considering the sum of anti-clockwise moment being equal to the sum of the clockwise moments. Remember, clockwise is how the clock moves, guys. The clock moves this way. This is the clockwise. Anti-clockwise like this, that is your anti-clockwise. So about L, we are considering R as it moves back to L. How is this going to move back to L? These are back to L. Which direction is this? That is our anti-clockwise. Remember, anti-clockwise, the way that it moves. What about 160 back to L? Look at this movement, clockwise. This movement, clockwise. This movement, clockwise. So meaning to say, it is only R which is going in the anti-clockwise to L. Remember, you're considering back to L. So R back to L is what? R times 15 meters. This is the only part that we have in the anti-clockwise. In the clockwise, we've got 160 back to L. There's a distance there. 160 times a distance of 1 meters, 2 meters back to L. 70 back to L again, 70 as it goes to L. That is 70 times how many meters? How many meters do we have in between? 2 plus 4, that is 6 meters. Plus, there is a 250 again, which is going in the which is going in the clockwise back to L. It is going in the clockwise. But the distance now, so 250 back to this, guys, that is the whole 16 meters, the 15 plus 1, which is 16 meters. So that's it. So that is taking moments about L. So you can consider this R times 15, that's 15R is equal to, combine everything on your calculator there. So that was going to give you 4,740 divided by 15. By 15, we have got our R. So that was going to be 316 Newton. So that is what you're supposed to obtain if you take your moments about L. So as we are told that we are supposed to take these moments about each support. So this time we are going to take our moments about R. Okay, so taking moments about R, let's see what's going to happen here. Taking moments about R. Okay, so this time still the movements, they are not going to change. And still our formula is not going to change. The sum of the anti-clockwise moment should be equal to the sum of the clockwise moments. So let's consider what's happening. L as it moves to R, take note of the direction. This is clockwise. It's the way clock moves. It maintains the way the clock. Okay. L, this 250, sorry, back to R as it moves. This is clockwise also. So which ones are going in the anti-clockwise? Let's consider these two. I want you to see what's happening. 70 as it goes back to R like this. This is anti-clockwise. The same with 160, anti-clockwise. So we have got two forces that are going in the anti-clockwise. The 70 and the 160. So 70 back to R, the distance now is what is the distance in between these 2 points? Between these 2 points. Remember, there we have got 2 plus 4, which is 6 from 15. So 15 minus 6, that is going to be 9 meters. So there we have got a distance of 9 meters. So that's 70 times 9 plus the 160 back to R. It's also anti-clockwise. So that is 160 times the distance. What is the distance? So remember, this is 9 plus this 4. So that is 18. So that is what we have in the anti-clockwise. What about the clockwise? So remember the clockwise, we have got 250 back to R, it's clockwise. So that's 250 times 1 meter. So this is equal to 250 times 1 plus we also have this IL, it moves in which direction as it goes to R? That's a clockwise movement. It's clockwise. So that's L times 15. It's a clockwise, that one. So it's part of the clockwise. So that's L times 15. So that's it, guys. You have got everything that you need. Combine the left-hand side, you obtain 2,710 is equal to 250 times 1. That is 250 plus L times 15, that's 15L. So you can take the 250 to the left-hand side, that's a negative. So this is going to give us 2,460 is equal to 15L. So that's it. You've got your L by dividing by 15 both sides. So our L in this case was going to be 164 Newton. So under exam condition, even if you are not told to prove, make sure that you prove these because you do not know whether these values are correct. So make sure that you do prove just to see if this is correct. Remember, to prove, we are going to use the concept that the sum of the upward forces is equal to the sum of the downward forces. So the upward are the reactions that you are given, the supports, the 316 and this 164 that we obtained. So is it equal to what is going down, which are those point loads that we are given? So the point loads, we are adding everything, 160, 70, 250. So if you add these three, what are you going to have? The 160, the 70, and the 250. That was going to be 480, and this was going to be 480 also. So meaning to say, our calculations, they are correct. They are correct. This is just to make sure that you are on the right direction, guys. Remember, this is exam. You have no one to say this is correct. So you can prove that and see if you are in the right direction, so that you know that at least you've got marks on that part or not. So that was our question 2, 10 marks. Then question number 3 on energy and momentum. State the law of the conservation of energy. Energy, remember, energy is something that we cannot destroy, that we cannot create. So that is the major part of this energy that we can consider as the law of the conservation of energy, that energy cannot be created. So energy cannot be created or destroyed, but can be converted to one form to another, from one form to another, but can be converted from one form to another, from one form to another. So you can convert energy from one energy to another, not to destroy or create it. 3.2, a motor car with a mass of 20 kilograms moves horizontally, all right, moves on a horizontal plane at a constant velocity of 15 meters per second. Okay, so let's see what's happening here. Let's see what's going on here. It has a mass. This is what you're given. It has a mass of 20 kilograms, moving at a constant velocity of 15 meters per second. That's initially our velocity is 15 meters per second. When the brakes are applied to bring it to stand still, means say there is no movement. The final velocity is now 0 within 6 seconds, which is the time frame. Within 6 seconds. Calculate from this information, 3.21, the acceleration of the motor car during the braking period. The acceleration. We talked of that formula before. You still remember? We still have our formulas here. We can even use the formula that we used previously. V is equal to U plus AT. Nothing has changed there. So we can still use the same formula because we've got this part of our linear motion. So from that part, V is equal to U plus AT. I mean, we actually made acceleration the subject. If you still remember, guys, it was V minus U over T. All right, so let's just substitute here V. That's 0 minus U, which is 15 over the time, that's 6. So remember, it's braking. As it is braking, it is reducing the speed. So meaning to say the acceleration is going to be a negative. That's negative 2.5 meters per square second because it is braking. So then from there, the braking displacement of the motor car. So the braking displacement, just like what we had before, the displacement. Only that your acceleration is negative. That's what they are trying to say. So this formula, I mean, this part of our linear motion is still to play a role. And also this acceleration that you calculated can play a role. So you can also think about this information where I'm given U, V, and T. Can I calculate the displacement? From the formulas that we are given, are we having a formula for displacement from that part? Okay, so if you check, so far we do not have. We have got this one, which I'm going to talk about, and also this one, it's going to work also. There's also this formula, which is not given on your formula sheet, that S is equal to U plus V over 2 times T. Also, you can use this because you have got U, you have got V, and you have got T initially here. You can use that. So that is, we can actually use that part. So S is equal to U plus V over 2 times T. Okay, so if you're someone who say, okay, what if I want to use those formulas that are given? Meaning to say you are limiting yourself to these formulas. I can use this. S is equal to UT plus half AT squared. Let's see. Can I have the same answer there? So we also have S is equal to UT plus half AT squared. Remember, I talked about this formula before. But when you are using this, because this one is direct, guys, I want you to use this one and prove if you are going to have the same answer. I'm going to explain this one because there you must be careful as you are substituting your values. That is your U, that is 15 times the time, which is 6 plus half of the acceleration. That is when it was braking, that braking acceleration as a negative times T squared, meaning to say we have got 6 squared. So you must consider the negative there. That's a braking acceleration that you had. So that was going to give us 45 meters at the end. So I want you also prove with that one and see what you're going to have. And also to prove with this one, you are going to have the same answer again, guys. All this v squared is equal to u squared plus 2as. With that one, it means you're going to use it this way. V squared is equal to u squared plus 2as. You can make this as the subject. So that's v squared minus this u squared. You divide by 2a. So divide by 2a, that is s. So you substitute again. You're going to get your s, which is the same answer, provided that the a is used as a negative as it is. So I want you to use these formulas, prove that it is the same answer. Not like you've got one formula. No, there's so many formulas. So many formulas. 3.23, sorry, that is to calculate the kinetic energy of the motor car before the brakes were applied. Before. That is when it was moving at 15 meters per second before the brakes are applied. That means they want you to use the initial velocity that was there. So what is the kinetic energy? Remember your kinetic energy, you also have it from your formula sheet. You've forgotten this. You can refer back to your formula sheet again. All right. All right, that is somewhere here. So remember that your kinetic energy is equal to half mv squared. Mass, we have the mass already. The mass is there, remember. The velocity we are using, the initial before the brakes were applied. The velocity that you are using there, that is the most important part. All right, so that's 3.23. So our kinetic energy, as we saw, the formula is half mv squared, but the velocity that you are using there is the initial before the brakes were applied. So that's why we've got the kinetic energy. So that's what they're testing you there. That's what they're testing you in this case. So it was going to be 2,250 joules. Remember, kinetic energy, you can also write in kilojoules if you want. Just divide that answer by 1,000. The momentum also before the brakes were applied, meaning to say we are still on that initial velocity. We are still using the initial velocity before the brakes were applied. But how do you calculate the momentum? Remember, the momentum is the product of mass and velocity. So that's 3.24, our momentum being the product of the mass and velocity. So that's the mass of 20 times the initial before the brakes were applied. So that was going to give us 300. Remember the mass in kilograms, the velocity in meters per second. So that's kilogram meters per second. Just like that. So you must be very, very careful how you answer your questions. On question number 4, we are given work, power, and efficiency. All right, so let's see what you're given. 4.1, we are given a lift with a weight of 980 Newton is lifted through a height of 12,000 centimeters. So convert this to meters. Remember, a meter has got 100 centimeters. So you divide by 100. That is 120 meters by means of a cable winding on a drum. The weight of the cable is, so I've got the weight of the cable per meter. That is 0.98 Newton per meter. All right, 4.21, calculate the total weight of the cable. So since we are given the weight of the cable per meter and we are given the total height of 120, we can calculate this. So that's 4.11. So our total weight of the cable in this case was gonna be the weight, meaning to say we are talking of the weight per meter times the meter. This weight per meter and per meter cancels. So that is 0.98 Newton per meter times how many meters? 120 meters. So like I said, this will cancel. So 0.98 times 120, that was going to be 117.6 Newton. Then from there, we are now asked to draw a fully labeled force distance graph using the given information. So in this case, I'm just going to show you a sketch of how you're going to have your diagram. So remember, your force distance is going to be of this nature. We need the force and the distance. All right, so this side is where you have got your force, which is in Newton. And this side, you're going to have the distance. So remember, this is taken at a weight cable. I mean, on our value of, that is 980, which is the weight of the lift in this case. So the weight of the lift is at 980. So you start with that one, which is your lift. That is at 980 Newton. So in this case, we know that it is going to cover 120 meters, the distance in between. So it's going to be from 0 to 120, or you just write 120 here. But taken at the total weight, which is the total of the two, the cable and the lift. So we need the total of the cable and the lift. So this will be the total 980 and the cable there. So remember, the lift is 980 and the cable has got a weight of 117.6. So this gives us the total of 1097.6 Newton. So meaning to say that is our total weight in this case, 6 Newton. Okay, so that is it. The displacement, the distance there shown like that. You've got you can obtain full marks with that, 3 marks. Just make sure that everything is properly taken. So you can even use a certain scale on this side. But here, look at these commas that you're given there. There's no need actually for you to have something that is accurate like that because of those decimals, okay? 4.13, calculate the work done in winding the total length of the cable with the lift attached to the cable, with the lift also attached to the cable, meaning to say we are considering the total work done. So the total work done is simply the area under the graph. So remember, you can use the area under the graph. Okay, so that's 4.13. So we are talking about the total work done. That is the total area. So we are talking of the total area under the graph. So if you know this shape direct, this is a trapezium, where we can simply use the formula for the area of a trapezium, half of the sum of the parallel sides times the perpendicular height. The sides which are parallel is this side and this side, they will never meet. So this side corresponds to the top of 1097.6 plus this side corresponds to 980 times the perpendicular height, which is the distance in between the parallel sides. That's a distance of 120. That was going to give us the total work done of 124,656 joules. You can even write in kilojoules. But since this is the area, you can also consider like the shapes differently. Thus, we've got a triangle on top. We also have a rectangle here. So you can also consider calculating of these areas differently. The area of a triangle separately, that is half base times perpendicular height. The area of a rectangle, which is base length times width, or base times the length that you're given, or you can consider length times breadth or length times width. So using this, we've got half of the base, which is this whole side, 980, times the height, which is the difference in between that we are given there. And that difference is the weight of the cable that we are given of 117.6. So that's 117.6. That's it. Plus You move on to the rectangle length times width or length times breadth. So that is 9 from this side. All right. That is gonna be, all right, guys, I'm considering 120. Where did I take this one? Here, this one. This is your best 120 there. Sorry for that. That is 120 there. All right, sorry for that. This is your length, 980 times the breadth or the width, which is 120. All right, so I want you to combine this and see if you are going to have the same answer. Or you can just consider your area direct like that using the trapezium that we are given there. So that was the first part of our section of the work, power and efficiency. Let's check the other part. So guys, let me just try and remove some pages in all these softwares. They tend to misbehave if you've got a lot of pages. All right, anyways, let's see what we have here. 4.2, a tractor moves at constant velocity of 42.2 kilometers per hour. The frictional force is, and also you've got the power. All right, so we've got the velocity, and you're asked to calculate the required to move. So this was supposed to be the required power. The required power there. Okay, so let's just see our information. We have got the velocity. So remember from that formula, whenever you're given kilometers per hour, you must change to meters per second. I talked about that here. 1 meter per second equal to 3.6 kilometers per hour. So divide that by 3.6. So 43.2 divided by 3.6 as our velocity. It was gonna be 12 meters per second. So we are given the frictional force of 2.8 kilonewton. The power of the engine of the tractor is the power of the engine. This is the input power of the engine, which is 160 kilowatt. So the question was 4.1, the required power to move the tractor at the above velocity, at this velocity that you are given. So this is like the output power now. So we are considering, in order for us to use velocity, remember power, we can calculate with force and velocity. We can calculate our power using force and velocity. Sorry for that, guys. You see what I was saying? That these softwares, sometimes they tend to misbehave. Oh, there's this one. All right, here. Power can be calculated from the force times the velocity, effective force and velocity. So with that, as long as you've got force, so meaning to say, in this case, our output power is going to be calculated from the frictional force times the velocity, as long as you've got force. So our force is the frictional force, that is 2.8 kilonewton times 10 to the exponent of 3 times the velocity, which is 12. So that was going to give us the output power, 33,600 watts. So you can even convert this to kilowatts, divide by 1,000. That's 33.6 kilowatts. If you want to convert to kilowatts, since this one is also in kilowatts, it's up to you. Then on 4.22, the efficiency of the system. So that is the efficiency. Remember, efficiency output over the input that we are given. Here we can consider, where is that formula? I want you to see it so that you can consider here. Whenever you're working with efficiency, that is output over input times 100%. So in this case, what is our output? It is the power. So meaning to say, as we consider of the output power to the input power times 100%. So that was going to give us the efficiency. The output power is the one that we calculated, 36.6 in kilowatts. You must also use this in kilowatts, which is 190. So that's 190 times 100%. So that's our efficiency there, which is 17.684%. So that is what you're going to obtain as your efficiency. 10 marks for that. I mean the whole question, not like that question only, but the whole question there. On question number 5, mechanical drives and lifting machines state Pascal's law in a closed system. What is it that you consider on your Pascal's law? Remember, when the pressure is exerted on the surface of the enclosed liquid, the pressure is transmitted equally in magnitude throughout the liquid in all directions. So it's all about the pressure that is being exerted on a surface which is enclosed. So it is going to be transmitted equally in that closed system that we are given. So that is our part. Then describe the effect of the depth and density of liquid on the pressure exerted on a liquid. So pressure is directly proportional to the depth and the density of the liquid if you consider this pressure. So remember that pressure is directly proportional to the depth. So it's to the depth. Okay, and also the density. And density of the pipeline. So that is what you are going to, guys, where am I getting this pipeline? The liquid that is inside. So you talk of the liquid there, okay? So with this, 1 mark is fine. All right, 5.3, we are given the following information refers to a compound gear train that consists of 4 gears. As we are given, the rotational of the gear A is 300. So we are given the rotational only of the gear A, which is 300 revolutions per minute. We are given the number of teeth on gear A, the number of teeth on gear B, the number of teeth on gear C, and also the number of teeth on gear D. This is what you're given. And from this information, the question is calculate 5.31, the rotational frequency of the driver gear B in revolutions per minute. B. Remember this relationship that you have between the gears and the number of teeth, the product NT. All right. So you can consider that, and you have, guys, this, you have got everything. NATA is equal to NBTB. So with that, we can formulate, okay? Remember, we want to calculate NB in this case. You are given TB, so you can use that. So that's 5.31 from this NA. So NATA is equal to NBTB. So remember, what we want is the speed at B, this one. So you can divide by TB both sides. Divide by TB both sides. So that means our NB was going to be NA, which is the speed at A. We are given 300 times TA, that is at A, we've got 25 teeth over TB, which is 60. So that was going to give us the speed at B in revolutions per minute. That is 120 revs per minute. So that is your question. And with the same part, we can answer the rotational frequency of the driven gear D. D is the driven, which is very true, driven by what? By C, which is on the same shaft with B, meaning to say they are at the same speed. The speed that we are seeing at B and at C is the same. So meaning to say at C, we also have the speed, which is the speed at B of 125 revs per minute. So with that, we can also consider to say the product, driver, product, driven is supposed to be the same. So NCTC in this case can work. So that's 5.32. So you're going to use NCTC is equal to ND TD. So that's it. What is it that you're supposed to calculate? That of the D, which is the driven. So divide by TD, divide by TD. So that's it. So that means our ND was going to be the speed at C. Remember, 125, same as the speed at B. So that's 125 times the number of teeth, which is at C. At C, how many teeth do we have? That's 36. So you're going to multiply by 36 over that at D. And at D, we have got 75 teeth. That means we're going to divide by 75. So that's it. The speed at D in revolutions per minute. That was going to be 60 revs per minute. That's it. So we've got 60 revolutions per minute. That is from this information. So each and every part that you're given, you must be careful of the formula to use according to the information that you are given. So I want us to check the other part of our question, which is 5.4. So they were given the power transmitted by a belt is 8 kilowatts. So we are given the power, the driver pulley with the diameter. So we also have the diameter there. So let's just see what is it that they want us to do. 5.4. So we have got the power of 8 kilowatts, the power, and we have got the diameter, 120 millimeters. So divide by 1,000. That means your diameter was going to be 0.18 meters at a speed of 600 revolutions per minute. The tension ratio of the tight side force to the slack side is 4:1. So that's T1 S to T2 is 4:1. Calculate the tension on the tight side. Okay, we are given the power. What is it that we can formulate there from the power and this whole thing that you are given? Remember that power is the effective tension times the velocity, and that Fe is equal to T1 minus T2. And that velocity can be calculated also. Where's that formula for pi dn? Okay, this one. You can also calculate your velocity pi dn. So we've got three things that we need to consider: calculation of the velocity and the application of that power. So we saw that velocity can be calculated pi dn. So meaning to say that is pi times the diameter in meters, 0.18, the speed in revs per second. That means we're going to divide by 60 to obtain revs per second. The answer of this whole speed must be in meters per second. That's why you have to convert these to revs per second. So in that case, you're going to obtain a velocity of 5.655 meters per second. But we saw that the power can be calculated. Why are we thinking of the power? Because that is where we have got this effective velocity times effective force times velocity. But the effective force is the difference of T1 and T2 times the velocity. So far we have got this, we have got this. We do not have T1 and T2. We need to calculate T1. Our question is to find T1, to calculate T1. But there is a ratio that we can play around there. T1 S to T2 simply means we can write T1 in terms of T2 or T2 in terms of T1. Since we want T1, so that means we are going to write T2 in terms of T1. It means T1 over T2 in that case is equal to T1, that is 4, T2, that is 1. You can write it as T2 over T1. It's up to you. T2 according to our ratio is what? It's 1. T1 according to ratio is what? It's 4. So meaning to say we can write T1 in terms of T2 or T2 in terms of T1. So what is it that you are supposed to calculate? The tight side, which is T1. So it's best for me to write T2 in terms of T1. So I can just multiply by T1 here. This cancels. So it means T2 is equal to T1 over 4. Why having this? So that we remove that T2 here with the T1, since we need to calculate T1. But if the question was calculate T1 and T2. You are not going to focus with the T1 or T2. You are focusing with anything. You can use whatever that you want. Even if you want, you can find T2, then use that, find T1. But avoid that. You can avoid it on the ratio. That's why you're given the ratio. Play around that ratio. So we can use T2 as T1 over 4 in place of T2. So let's substitute the power 8 kilowatt. That means 8,000 power is equal to T1, which is the one that you are supposed to calculate, minus T2 in terms of T1. That's T1 over 4 times the velocity we calculated, that's 5,655. So you formulated an equation from there that you can use to calculate T1. Guys, 1 over 4 is simply like 0,25. So you can even subtract these two. These are like terms, T1 and T1. So you can subtract 1 minus 1 over 4. That is 8,000 is equal to 1 minus 1 over 4, or 1 minus 0,25. That's going to be 0,75. So we've got 0,75 T1 times the 5,655 that is outside here. What you need is T1. So what is affecting T1? You remove that. If we check properly here, what is affecting T1 is these two terms product. So how do you remove it? Divide. So T1, going to divide 8,000 divided by what is multiplying, which is 0,75 times this, 5,655. The solving there later on, guys, it's in your hands. It's in your hands. You're going to solve the way that you want. So it's going to be, according to mine, it was going to be something like this in Newton, just like that. All right, so that was 4 marks for that. Let us consider 5.5, a differential wheel and axial lifting machine. Here's the following diameters. The wheel diameter, remember, this is your D, the wheel diameter. 320 millimeters divided by 1,000. That's going to be 0,32 meters. The big axial diameter, that is your D1, divide by 1,000 again, 0,28 meters. And the small axial diameter, that's our D2, divide by 1,000. That's it. So the question on 5.51 was to calculate the velocity ratio of the lifting machine. With this, remember you're given the velocity ratio is given as 2D over D1 minus D2. So there, guys, it was not gonna be any effect there. So that's 5.51. So guys, our velocity ratio is given from there 2D over D1 minus D2. So guys, revise, know your formula sheet, understand your formula sheet. So 2 times D, 0,32, everything over D1 minus D2. So that's 0,28 minus D2, 0,19. So that was going to give us the velocity ratio of 7,111, like that. All right, let's consider the other part, 5.52. The mechanical advantage if the effort is, so we are given the effort there. So let us just take our information. So we have got an effort of 400 Newton to lift a load of 190 kilograms. So we have got the load. Remember, this is supposed to be in Newton. So it's supposed to be mass times gravitational acceleration. So that's 190 times gravitational acceleration of 9,8. So that was going to give us the load, to lift the load of. So you also need to know that load. So that was 1,862 Newton. All right, so the question was, what is the mechanical advantage there? So the mechanical advantage can be calculated as the load over the effort. So you can use our formula. So already there, load over effort. So in this case, our mechanical advantage, load over effort. That is the load that we calculated now, 1,862 over the effort, which is 400. So that was going to give you the mechanical advantage of 4,655. All right, so that's 4,655. So that was it on this part. Then the last part of our question was the efficiency of the wheel and axle lifting machine. We need the efficiency of this machine. So from what we just calculated, we can obtain our efficiency from the mechanical advantage over the velocity ratio that we calculated times 100%. So we have got everything there: mechanical advantage, velocity ratio. So we can calculate that efficiency. That's 5.33. So our efficiency from this, we've got mechanical advantage over velocity ratio times 100%. Meaning to say there, our mechanical advantage 4,655, the velocity ratio 7,111, like that. Then you multiply to 100%. That's the efficiency percentage now that you are obtaining. So that was going to give us 65,462%. So you've got the efficiency of the machine in that case. So you must be careful the information that you're given, the formulas that you are working with. So in this case, for 17 marks, the whole of this question, it was fine. Just have to make sure you work with more questions from there. Do revise as much questions as you can. On question number 6, which is friction, we are given define the term static friction. The static friction. So as you know, the static is the frictional force resisting, which is the frictional force resisting up the motion up to the point of sliding. So you can refer that way as it is the frictional. It is the frictional force that is resisting, okay, resisting motion up to the point, in this case of sliding, up to the point of what? Of sliding. Yeah, so let me know, guys, any other way that you can define this. So many ways or simpler terms that you can actually use. A stationary trailer with a weight of 640 Newton is loaded with 10 bags of cement, each weighing 80 Newton. All right. Thus, we have got a weight combined there. There's something that is the weight on its own of the trailer, which has 640 Newton. Then the cement, which is inside, there are 10 bags, each has got 80 Newton. So 10 times 80, that is 800 Newton. So what is the total weight? So our total weight, the trailer with what it is carrying, it is going to be 640 plus 800 together combined. You add. So that was going to be 1,440 Newton. So this is the one that we are going to work with. So they are saying this trailer is on an inclined plane at an angle of 25 degrees, this and that. All right. So guys, this is what you have considering. This is on an incline. So we've got something like this, 1,440 Newton. Remember, we have to add everything to obtain this total weight that you're given here. So inclined at an angle of 25 degrees, which is our theta, to the horizontal, the coefficient of friction And also we have got that of 0.43. We have got the coefficient of friction 0.43. So as we know that we're going to have that part which is parallel to the plane, the part that is perpendicular to the plane, meaning to say we have got our W in this case, which is equal to mg. Already, this is what we have calculated. So with this information, guys, it was enough for us to have anything, guys, just it's enough. 6.21, the weight component parallel to the plane. If you have forgotten, your formulas, they are there. So the one that is parallel, that's your Fs. So Fs is equal to W sine theta. From there, we can calculate the weight component parallel. All right, so that's 6.21. So that's Fs, or you can write it as F parallel this way. Or you can just write it as what? As Fs. It's just one and the same thing. Same with this one. It's the same as Fc. So that is W sine theta, which is the weight. Already we've got that 1,440 times the sine of the angle of incline of 25 degrees. This was going to give us 608,570 Newton. So that is your Fs. And in that case, we can move on to another question. The weight component perpendicular. That is, we are considering our Fs, perpendicular W cos theta. All right, so everything there is just a matter of substituting to what we are given. So the 6.22. So Fc, that is W cos theta, 1,440 times the cos of theta, which is 25 degrees. So that was going to give us 1,305,083 Newton. So that's your perpendicular, all right, component in that case. And the frictional force, we can calculate this from this formula. All right. There we have got this relationship that the coefficient of friction is the frictional force over the normal reaction. So in this case, we are going to use Fc when it is on an incline, which is the perpendicular component that you calculated before. So let us make this, because we have got our coefficient of friction there. Just going to make it the subject. So the 6.23. So we saw that the coefficient of friction is equal to the frictional force over, so it's going to be perpendicular this time. You use the perpendicular component. So the frictional force is just going to cross multiply. Thus, the frictional force is equal to the coefficient of friction times Fc. That is the one that we calculated. Remember, your coefficient of friction 0.43. We are given this. So that means we're going to have 0.43 times Fc, 1,305,083. So the product of these two is enough to give us the frictional force, which was 561,186 Newton. That's it, guys, for 2 marks. It's enough for 2 marks. 6.24, the force required to pull the trailer up the incline. Up. So as it is going up, we're going to add. So this is the sum. So on your formula sheet, you must be careful which one is going up, which one is going to appear. So when it is going up, that's your frictional plus Fs. When going down, you take the negative. So in this case, we are going to focus with the positive as it is going up. As it is going up. So F up, that is the sum of those two. In this case, all right, the 6.24. So F up is equal to the frictional force plus that Fs, which is our parallel component. So that's frictional. We got 561,186 plus our parallel Fs, that is a 608 608,570 that we got before. So we've got 608,570, that one. So that was going to be 1,169,756 Newton. So that's it. We have got our F up. So make sure that you do understand how the question is given, the information that you're given there, like there you had to combine is the load, or is the weight of the cement and the trailer which is carrying that cement. So it becomes your total weight in that case. So you see how they try to confuse you guys. In that case, if you're someone, you're going to use that as the weight of the trailer only, which is wrong. Unless if you are told that when it is empty, to make calculations when it is empty, there you use the information the way that it is given. They have specified when it is like, but in this case, you are going to use as it is, that information as it is. All right, so let's see our part 7, which is question number 7 on heat. 7.1, define the term heat capacity. So the heat capacity you can consider as the amount of heat required. That is the amount of heat required to raise. So it's gonna raise the temperature, to raise the temperature of the entire mass, of the entire mass of substance by 1 degree Celsius. So this is gonna be 1 degree Celsius, or it can be a Kelvin. So that is what you were given. 7.2, we have got this question. You were supposed to be very, very careful the way that it was given them. They are saying 25 liters of petrol burnt for 2 hours. So that is, we have got the volume there. This is the volume. Remember, volume can be related in terms of liters. A liter is equal to 1,000 cubic meters. That is what you are going to have that consideration, or you're going to consider it in that manner. Actually, we consider this, a cubic meter. Very sorry for that. Very sorry for that. 1,000 liters. A cubic meter. It's 1,000 liters, 1 kiloliter, not the other way that I had there. So 25 liters, it means can be converted to volume. That is 25 over 1,000. Okay, so there we have got the volume of this petrol that we are given. So that's going to be 25 over 1,000 times 1 cubic meter times this. So it's going to be 0.025 cubic meters. We have got the volume there from that. What else are we given? It is bent for 2 hours. That is the time frame. 2 hours. Okay, we can convert this to seconds depending on the information we'll see later on. Assume the density. So we are given the density as 740 kilograms per cubic meter. So there, they wanted you to understand this relationship between the volume and the density. Remember, from this MdV concept, from our MdV like this, that's the mass, the density, the volume. So in our calculations, we need the mass. So it follows that we are also having the mass in this case, which is the density times what? Times the volume. So density times volume gives you the mass. So this density of 740 times the volume of 0.025 gives us the mass of this petrol, and that is something like 18.5 kilograms. Okay, so let's see our question. It was from this information, calculate 7.21, the energy released by petrol. So we need the energy released by the petrol. So as we do understand that we can calculate our energy from the product of the mass here and the heat value. So you can consider energy from the mass and the heat value concept. So meaning to say we can have this, remember, it is given petrol. So let's go back here. Let's go back again. We're gonna need, let me just remove this, guys. Remember this thing, guys, I need here. I need this one here. So considering this, the heat value of petrol, that is 25 megajoules per kilogram. So there it is 25 megajoules per kilogram. So mass times heat value, but remember your heat value there, 25 megajoules. So that was gonna give us, in this case, the energy. So 7.21 Q, which is our energy mass times heat value. So you can also write this as E is equal to the mass times the heat value. Remember, you calculated the mass, 18.5 times the heat value, which is 25 megajoules. So that's 25 megajoules per kilogram. So remember, this mass is in kilogram. So per kilogram and kilogram cancels. Your answer is direct in megajoules. So that was going to be 462.5 megajoules. So this is the energy released by the petrol. The equivalent power of the petrol in kilowatts, the equivalent power. So power, that is Q over T, from this energy that we calculated, that is power, can be calculated. So guys, you have got your formulas, everything. Just know how to use your formulas. Since you've got the time there, you can use this formula. So that's 7.22 power being equal to Q over T. So that is our energy and the time in seconds, so that we obtain the joules per second, which is power. So that is the energy. If you use this in megajoules, like what you are given, you are going to obtain megajoules per second, which is megawatts. Okay. If you do not want to do that, you can just write as it is, 462.5 times 10 to the exponent of 6. It's in your hands. Okay. So that is the time, 2 hours in seconds. Remember, in an hour, we've got 3,600 seconds. So 2 seconds, you're going to multiply by 3,600, or 2 times 60 times 60. 2 minutes, 60. 2 seconds, you multiply again by 60. So this was going to give us the power, which is 64,000, actually 236,111, like this, in watts. So that's it. You can convert to kilowatts. It's in your hands after that. All right, then we are given 7.3, a wire with a length of 35 meters at 11 degrees Celsius expands by this. All right, so that is initially, we have got the original length in this case, the 7.2. We've got the original length of this wire at 35 meters at this, that is the initial temperature, 11 degrees Celsius. It expands by, that is the change in length, 15 millimeters times 10 to the exponent of -3. That will be 0.015 in meters. If the temperature rises to, if it increases to this value, that's we have got the final temperature at 20 degrees Celsius. So it's from to initial final. So the question is, of this information, calculate the coefficient of linear expansion of the wire. Calculate the coefficient of linear expansion, which is alpha. So know that from the change in length, there we have got the linear coefficient of expansion alpha. So the change in length is equal to the original length times the linear coefficient times the change in temperature. So with that formula that we are given, we can even manipulate that alpha that we want. Just divide by the original length, the change in temperature, both sides, original length times the change in temperature. So that was gonna cancel. You remain with the coefficient, the linear coefficient of expansion. So that's the change in length. You have it. That's 0.0. In this case, the change in length, you have it 0.015 meters over the original length, 35, times the change in temperature. Remember the change in temperature, that's T2 minus T1. So we are going to subtract T2 minus T1, the change in length. So that was going to give us the linear coefficient of expansion of 0.0000 like that, 476, something like that, per degree Celsius. So that's it. Can even leave your answer like that, guys, for 2 marks. Just leave it like that. Let's see the other part. 7.4, explain the term saturation temperature. What is the saturation temperature? So the saturation temperature is the constant temperature at which liquid changes in phases from liquid to vapor at a given pressure. The constant pressure at which liquid changes in phases from liquid to vapor at given pressure. Different types of steam are produced as the temperature of water rises, as the temperature is increasing. Given these temperatures, from the initial saturation up to the superheated, name the types of steam at points A, B, and C. At A, B, and C, what is the type of steam that we are having there? So remember, at A, this is wet steam. The steam is still wet. At B, we are now talking of the dry steam. And here we are talking of the superheated steam. That's it. So that was what you were given. So make sure, guys, you do understand the presentation that you're given. In N3, you are going to have a continuation of that diagram. So here they just want you to know those basics. Then define the resistivity of a conductor. What is it that you are to consider? That is our question. All right, guys, there is a section that was actually on that part, and I removed it. It was on the chemistry. Okay, let's just hope we're gonna find time to talk about that. But anyways, like you can't reverse. Once you delete that page, you can't reverse it. I'm seeing that I removed it, was just down there. So this is it, guys. Anyways, let's see. So there, the resistivity of a conductor, what is it that you are considering? The resistance measured between two opposite faces of a unit cube of the material at a certain temperature. So it must be taken at a certain temperature. So 9.2, you're now asked to briefly explain how the length and the cross-sectional area of a conductor, that one that you're talking about, influence the resistance of that conductor. So remember that the resistance is equal to rho L over A. So what is happening? The length, the resistance, they are directly proportional. So the length, this one, it is going to affect directly. So this one is directly proportional. So the length is directly proportional. What about the area? It is inversely proportional. So this is inversely proportional. So meaning to say, as the length increases, the resistance also increases. But as the area increases, it opposes, the resistance decreases. That is to be inversely proportional. As another part is increasing, another one is decreasing. But the other part, it's an increase to an increase in the length and the resistance. So that's what they wanted there, to tell the relationship. They were given to study the circuit below and answer the questions that follow. So this is our circuit from positive, negative. All right, the resistor, the current here is going to enter this resistor. All right, from the total current that we are given, it enters this, and this branches to these two resistors, R2 and R3. You're having current 3 here, current 2. Okay, resistor 2, current 2, resistor 3, current 3. This is the total current from the supply. All right, so they were given resistor R1 is 3 ohm, R2 is 2 ohm, R3 is 3 ohm. So R1, remember, it is 3 ohms. This is what you're given. And also the current I2, the current flowing this resistor is 1,2 amps, and the total current being 2 amps, which is the total current here being 2 amps. First question, it was calculate 9.31, the resistance of the resistors connected in parallel. These two resistors that are, sorry for that, these two resistors here in parallel. That is our question. So the resistance in parallel, there you're going to consider, you can consider even the product over the sum. You can consider that product over sum. We're going to consider another formula again, but you can use product over sum. The product of these two resistors, R2 times R3, over the sum R2 plus R3. So that's it, R2 times R3 over R2 plus R3. So that means this was going to give us the parallel resistance of 1,2 ohms. Or remember that in a parallel combination, the total resistance can be taken from the formula 1 over Rp is equal to 1 over R1 plus 1 over R2 and so on. But in this case, we are considering R2 and R3, so it's going to be 1 over R2 plus 1 over R3. So that means 1 over Rp is equal to 1 over R2, which is 2, plus 1 over R3, which is 3. So if we were to add this on your calculator, that was going to be 5 over 6. So how do you find Rp, which is the resistance? Just find the reciprocal of this. Just divide 1 over this. That's the reciprocal. So it was going to be 6 over 5. That is the parallel resistance, which is 1,2 ohms. So in parallel, our resistance was 1,2. Then the total resistance of the circuit, the total resistance, you are now combining with R1. Remember, you combined these two, then to R1, they'll be in series. So in this case, the total resistance, it will be R1 plus the parallel combination that you are given. So that's 9.32. So the total resistance, we're going to have R1 added to the combination of the parallel combination that you obtained. So that's it. R1 is 3 ohms. So you're going to have 3 plus this 1,2. So that was going to give us the total resistance of the circuit, which is 4,2 ohms. Okay. Then another part of our for question here, it is to calculate the current flowing through resistor R3. The current through resistor R3. According to this circuit that we are seeing here, there is a current that we are given as the total current, which is branching into two currents that we are given on our circuit I1, I2, and I3. From the total current here that we are given, this current, it flows, this one enters here, another one enters there. So from your Kirchhoff's law, you can calculate this. Remember that the Kirchhoff's law from your industrial electronics N2 states that the total current that is entering into the branch is equal to the currents flowing away from that branch, which is the junction I2 and I3. The current flowing towards the junction is equal to the current flowing away from that same junction. So with this, you can calculate I3. Okay, transpose I2 to the other side. That's IT, total current, minus I2 is equal to I3. So that means I3 is the total current. Sorry, the total current here, which is 2 amps. So that's 2 minus I2, which is 1,2 amps. So with this, you're going to obtain the current across resistor R3, which is I3, and that was going to be 0,8 amps. Remember, current is measured in amps. So make sure of what you are writing there. 9.4, we are given, give 2 practical applications of electromagnetic induction in practice. Where do we apply this? Remember, you can use this in the application of the generators, the transformers. You can have this in transformers. We can have this in electric motors also. These are applications that we can consider in our syllabus. All right, then 9.5, give 2 examples of insulators, those materials which do not conduct electricity. Talk of wood, plastic, all these materials which do not conduct electricity. Talk of a rubber. We also talk of the pure water, the glass, so many things that we can consider as our insulators. So that was our total 100 in this case of the paper, which was written April. So make sure that you do revise as you prepare for your exams, which is for the August or November exams that you're going to have. This is going to help because most of the times they do repeat these questions. So make sure that you understand each question so that if they do repeat that question, you have got an advantage. So these are the typical questions that you might have on your engineering science N2.